Greetings! In the previous video, I showed you the RF flow, so radio frequency signals flowing into the transverters from the shack up to the tower, through the transverter system, out and then back into and receive and then down to the shack. And I also showed you as a teaser a high-level control diagram of the entire system. Now today, we're going to dig into the details of controlling this system. Now, in order not to scare you away, I will start with the shack controller, which is much simpler. If you recall, I mentioned in the previous video that we would have a computer controlling the entire system, and that's the interface to the whole system. It's from the computer to the shack Raspberry Pi Pico, and I use a USB to UART converter into a regular UART. I don't use the onboard USB connector. The reason is I want to reserve the onboard USB connector to reprogram the Raspberry Pi Pico when necessary and segregate the communications onto a separate UART and separate communication channel, just to keep the USB port for reprogramming if necessary. So that's the communication with the PC. On the other side, so facing the tower and to the remote controller, I am using RS485. It's one single twisted pair, so it's a simplex system I've decided to use, so one message at a time, so a single pair of wires will allow me to communicate in both directions. I'll have around 20 meters of cables, and that should be okay on ordinary rotator cable for speeds of like 115 kilobits per second or even 230 kilobits per second. It will be just fine, I'm pretty sure. And for the conversion, I use a THVD 1406 RS485 transceivers, and it of course connects to another UART port here. Now, facing the IF radio, I have two connections. I detect the PTT through a transistor interface, so a logic level low indicates that the push to talk on the IF radio is depressed, whether it's Morse code sent or the PTT on the microphone. I detect this into the shack Pico, and that message is sent up to the tower, of course, and also to the computer. Up on the tower, when everything's ready to transmit, another message is sent to this shack Raspberry Pi Pico, and that Pico will allow the radio to transmit RF by releasing the negative ALC voltage. That's the only way we can really inhibit the RF from sending out when the radio is in transmit, is by sending a negative voltage to the ALC line, which pretty much cuts off any RF. But when everything's ready, we can release that negative voltage. Okay, so open the solid state relay and let this thing go free, and then the radio will start sending RF up to the tower at 144 megahertz. Now for the solid state relay, I use Panasonic AQV 214 solid state relays, same device I used in the portable 10 gig system that I designed last year. It works very well. It can control up to 550 milliamps, and it's relatively cheap. And it's just a DIP 6 package, so really useful. So that's pretty much what's going to be on it, other than a 5-volt regulator, of course, from 13.8 volts, the station 13 volts, and also a minus 5 volt. That's the minus 5 used for squelching the ALC. So it's a plus 5 to minus 5 converter. So that's the local shack controller. Now some of it will repeat on the remote end. Okay, so do not jump, please. I'm switching to the next chart. Alright, so this is the remote controller based on the same Raspberry Pi Pico board, populated differently with different components, but it's the same actual board. Different software, of course, will be running on this remote Raspberry Pi Pico. I mentioned that there were common things with the local controller, such as RS485 link here, and the use of AQV 214 solid-state relays, a plus 5 volt regulator, of course, but there's much more on this system. Namely, a combined DAC and ADC chip. It's one chip, the AD5593, which will allow me to send analog voltages and read analog voltages. What is it gonna send? As far as analog voltage, I'm going to be able to tune the ovenized oscillator that's on the same board. And this is the 10 megahertz reference that will sync everything, my whole RF chain. So it's a small can, but it's ovenized oscillator. And I will be able to tune the 10 megahertz frequency exactly to the right frequency so that I put out 10.368 exactly using the DAC output of that chip. And I'll also be measuring the various voltages, plus 8 volt, which is pretty much the voltage used on the whole RF strip, plus 8 volt receive, plus 8 volt transmit. It's the same constant 8 volt produced by a low drop-off regulator, but it will be switched using AQV 214s. And if one of these AQV 214s goes belly up, I'll be able to measure that the 8 volt is not present. So that's why I'm measuring these. And I'll also be monitoring the RF output. That's the nice thing about this power amplifier, is it has an analog voltage that we can measure that represents the RF output. It's a diode detector, so it's not linear, but you can easily chart it if you like and measure the voltage to figure out how much power you're putting out. So that's what's going to be measured on the combined DAC ADC chip, and this is I2C, so 2-wire control. I have an additional AQV 214 here, a solid state relay, to control a fan. It would definitely be a 12 volt fan placed on the 10 volt bus, because the 10 volt is the main bus on my system. So 10 will be enough to make the fan run. And some small fans draw only a couple hundred milliwatts, so an AQV 214 is good enough for that. I'll have control to the steering actuator through an actuator control board. This is off the shelf, bought on AliExpress, with 2 PWM pulse width modulation lines. I will be able to control the power sent to the actuator to steer the dish. Low speed, high speed, depending on the duty cycle of the pulse width modulator sent to this controller board. And the board needs plus 10 volts, the main bus, and 3.3 volts for the control side facing the remote Raspberry Pi Pico. I'll also have the ability to measure temperature. I've decided to put 2 LM75 temperature sensors. I could put as many as 8, I believe, on the same I2C bus, but 2 should be enough. One will be attached to the power amplifier heatsink, and the other one will measure ambient air temperature, so it'll be floating in the air. One additional signal that I will be monitoring is my synthesizer board lock signal. When it's in lock, it gets 10 megahertz from the isotemp here into the synthesizer board, and it produces the 3408 megahertz signal. When it's in lock, it produces a high level on one of the control pins. And I do monitor that pin to make sure that the system is in lock. If the synth board is not in lock, I'm dead in the water. Nothing will work on the transverter. So it's important to know that this is working. Otherwise, what's left to explain? The synth board and the tripler board always get plus 8 volts, so it's always on, whether we transmit or receive. It's always on. The other sections will receive either transmit or receive depending in what mode we are. So these voltages are sequenced by the Raspberry Pi Pico through the AQV 214 solid state relays. And there's a coaxial relay. 8 volts for this guy is not enough, so I'm using 10 volts straight into the transmit receive coaxial relay. That's the 10 gigahertz relay at the antenna. And finally, in order to place the power amplifier into transmit mode or receive, I need to toggle a control line to low for transmit and high for receive. It's just a TTL line, nothing special, but I'm still going through an AQV 214 solid state relay and ground and transmit. And this guy, the power amplifier, gets the plus 10 volts directly from the main bus. It requires around 7 amperes of current in transmit mode, whether we send RF into it or not. So that's the configuration of a control diagram, as simple as I can draw it. Of course, this is converted into a circuit schematic to produce a little board. And you know what? I'm going to skip that step. I'm not going to show that thing to you. If someone really needs it, they can contact me and I'll provide the KiCad files. It's essentially what you see here and here combined on the same PCB. You'll get a chance to see the PCB when I do the system test. You'll see the PCB, what it looks like. Alright, all for now. In a future video, I'll show you the power distribution block diagram. Thanks, 7-3.